Further mechanics, circular motion. You're going to be studying the mechanics of motion in a circle, which leads on to something called simple harmonic motion and also to gravitation and explaining the orbits of planets and satellites. Before you go any further, I want you to make a note that this is in your purple textbook, page 223 to 229. So at some point before I see you in September, you need to read through that, make some notes, do the questions and self-assess that from the answers. There's a video that I want you to watch. I will put the link on Teams for you to access. I want you to watch that video and make some notes on it, and then come back to this video. Radians are going to be very important in this topic. You've met radians before when we did waves. So a quick refresher. The circumference of a circle is 2 pi r. Radian is based on the arc length. If the angle is 1 radian and the radius is r, then the arc length is also r. That gives us a conversion where 360 degrees, well, the circumference is 2 pi r, so that must be 2 pi radians in a whole circle. Angular displacement and angular velocity are vectors. Now, regular displacement and regular velocity, so linear displacement and linear velocity, those are vectors. Angular displacement and angular velocities are also vectors. So displacement is distance with direction, and linear velocity is the rate of change of displacement, so change in displacement over change in time. Angular displacement, instead of being meters, it's radians. It's a change in angle. It's the angle that's rotated through relative to the starting axis. Angular velocity is the rate of change of angular displacement. So it's how quickly the angle is changing. The angle is in radians, so the units of angular velocity are radians per second. So let's have a look at how linear velocity and angular velocity are related to each other. The distance covered by an object moving in a circle in one time period is the circumference of the circle. So if we do speed equals distance divided by time, the distance is the circumference and the time is the time period. So the linear velocity is 2 pi r divided by t. Angular velocity, we need to look at the angular displacement. In one time period, the object moving round in a circle will have an angular displacement of 2 pi radians. So the angular velocity is 2 pi over t. We can combine those two equations. If omega, that's the angular velocity, equals 2 pi over t, then v must be 2 pi over t multiplied by r, so v equals omega r. Another reminder about frequency and period from waves in year 12. Frequency is the number of rotations per second. Time period is the time taken for one rotation. So period is 1 over frequency, and frequency is 1 over time period. But we know that the angular velocity is 2 pi over t. But if f equals 1 over t, then omega must be 2 pi f. So omega is sometimes referred to as angular frequency. as well as angular velocity. When we do circular motion, we'll tend to call it angular velocity. When we're doing simple harmonic motion in year 13, we'll tend to call it angular frequency, but they are the same thing. So here's an example. If you're feeling confident, pause the video and try working it out and then come back to the solution. If you'd rather just have me talk you through it, that's fine, just keep playing. So a cyclist is travelling at a speed of 28.8 kilometres per hour along a road. The diameter of his front wheel is 68 centimetres. What is the angular speed of the wheel? And how long does it take for the wheel to turn one complete revolution? In other words, what is the time period? Well, the speed of 28.8 kilometres per hour, the first thing we need to do is convert that into metres per second. So we need to multiply by 1,000 to turn the kilometres into metres, and then divide by 3,600 because that's how many seconds are in an hour. So the linear speed comes out to be 8 metres per second. In a previous slide, we saw that v equals r times omega, therefore the angular speed, omega, must equal v over r. R is the radius, so that's going to be 0.34 of a metre because the diameter is 68 centimetres. We want that in metres, 0.68 metres, half of that, 0.34. So the angular speed, or the angular velocity, must be the linear velocity divided by the radius, 8 over 0.34, which comes out to be 24 radians per second. The time to complete one revolution, well, one revolution is 2 pi radians. So the angular displacement is 2 pi radians. The velocity is 24 radians per second, which works out to be 0.27 seconds. I want you to pause the video now, do these 5 questions, and then come back to the video for the answers. If you're struggling to see these on the screen, there's a version uploaded onto Teams that you can use. Have you paused the video? Okay, ready for the answers? Pause the video and mark your work. If you got questions wrong, make sure you work backwards and try to find out what it is that you did. Ready to move on? I want you to pause the video again, do these questions. Pause the video now. Are you ready for the next set of questions? Pause the video now and do these questions, then come back and mark your work from the answers on the next slide. Are you ready for the answers? If that's too small to see, there is a version of the PowerPoint on Teams that you can use. So pause the video and mark your work. Are you ready to move on? Now we need to look at acceleration and forces in circular motion. Any object moving in a circle has got a changing velocity. Because the direction is changing. Remember, velocity is a vector. It is speed in a certain direction. If the direction is changing, then there is an acceleration. The object that's going around in a circle is always moving along the tangent to the circle. So imagine this little fairground ride doing a loop-the-loop. The velocity is always a tangent to the circle. And I want you to imagine having a mass or a weight on the end of a string and you're whirling it around above your head. If you let go, the object is going to fly off in a straight line. It's not going to keep going round in a circle. Think again about the object going round in a circle. If you're holding onto a string, you're pulling it always towards the centre. So there must be a force and therefore an acceleration towards the centre of the circle. Now, acceleration is rate of change of velocity. That's going to be important. Any object moving in a circle must be accelerating. That acceleration is directed towards the centre of the circle. So that's why we call it centripetal acceleration. Centripetal means centre seeking, so directed towards the centre. Please don't get it confused with centrifugal forces. Think about it, centrifugal would be going away from the centre. This is centripetal. The force that's pulling it around in a circle is directed towards the centre of the circle. Okay, we're going to derive an equation for the centripetal acceleration. So here we have our circle. And we have an object on that circle, which has radius r, and it's travelling at velocity v1. That's its linear velocity. A little while later, the object has moved around the circle, so its velocity is now v2. It's the same size, but the direction has changed. And the angular displacement is theta, so it's rotated through a certain angle. Now, change in velocity would be v2 minus v1. So all I've done there is I've taken v1, that vector velocity, and I've turned it upside down to give me minus v1. That's all I've done. So v2 there, if I add v2 and minus v1, the change in velocity is v2 minus v1. It's represented by that kind of gold coloured arrow there. And that has got the angle theta between v2 and minus v1. So we have similar triangles. Okay, the arc length between those two positions is v delta t. So the linear velocity times time. Now we're going to use a small angle approximation. We're going to assume the angular displacement theta is so small that the arc length is effectively a straight line. Then, all I've done here is I've reproduced that triangle. There we go. So instead of having a curved arc length, because we're saying, well, theta is so small that the arc length is effectively a straight line, I can replace it with a straight line. Now those are similar triangles. Therefore their sides have the same ratio. So v1 and v2 have the same magnitude, just different directions. So the gold coloured arrow there, delta v, divided by either v1 or v2, because they're the same length, delta v over v, must equal v delta t over r. So taking my yellow coloured triangle and my blue coloured triangle, just saying those are similar triangles, So the sides are the same ratio, so delta V over V must be V delta T over R. I can rearrange that. If I cross multiply, I get delta V times R is V times V delta T. If I rearrange that again, I get delta V over delta T equals V squared over R. But that's acceleration. So acceleration is V squared over R. All right, A equals V squared over R. But we know that V equals R omega. That came up much earlier. So if we replace the V with R omega, we get acceleration equals R omega squared divided by R, which leads to A equals R omega squared. So we can work out acceleration whether we know the linear velocity or the angular velocity. This would be a good point to go and have a look at the full A-level version of the Data and Equations booklet and find all these equations on there. Getting the equations for force is nice and easy. We know from Newton's second law, which officially says force equals rate of change of momentum, but that will simplify down to F equals ma. So if A equals V squared over R and F equals ma, then F must equal mv squared over R. Similarly, if A equals R omega squared and F equals ma, F must equal mr omega squared. So once we've got equations for acceleration, we can get equations for the centripetal force. Just got to remember, the acceleration and the force act in the same direction as each other, but the velocity, linear velocity, is at right angles. It's perpendicular to the acceleration and to the force. Here's a worked example. If you're feeling confident, pause the video, do it, and then come back. If you just want me to talk you through it, that's fine, just keep playing. So we have a car of mass 890 kilograms moving at 15 meters per second. It travels around a circular bend of radius 18 meters. Calculate the centripetal acceleration and the centripetal force experienced by the car. Well, acceleration equals V squared over R, 15 squared over 18, which is 13 meters per second squared. The data is all given to two significant figures, so we give the answer to two significant figures as well. Force, well, we've got the acceleration, we've got the mass, we can't just do F equals ma. Again, two significant figures is appropriate, 11,000 newtons. Here's another one. Pause the video if you like, have a go at it, and then come back for the answers. Or just keep playing. A satellite orbits the Earth twice every 24 hours. The acceleration due to Earth's gravity is 0.57 meters per second squared at the satellite's orbiting altitude. How far above the Earth's surface is it orbiting? The radius of the Earth is 6,400 kilometers. Just going to point out something that might be obvious. Earth's gravity is only 9.81 if you happen to be standing on the surface. If you are in a satellite orbit, the gravitational field strength decreases with distance above the surface. So it's not going to be 9.81. Okay, how far above the Earth's surface is it orbiting? Let's work that one out. Let's see. Well, orbits Earth twice every 24 hours, so one time period is 12 hours, but we need that in seconds. There's 3,600 seconds in an hour. So 12 times 3,600 gives us 43,200 seconds for the time period. The angular speed is 2 pi over the time period, because one full circle is 2 pi radians. So 2 pi divided by 43,200 gives 1.45 times 10 to the minus 4 radians per second. The acceleration is omega squared r. So the radius must be a over omega squared. A is the acceleration due to gravity. That's its centripetal acceleration being caused by the gravitational attraction between the satellite and the Earth. So A over omega squared gives us 26,945.2 kilometres. We've done a sneaky little unit conversion there without telling you. But we're asked for the height above the Earth's surface. That value that's just been worked out, the radius of the orbit, that's the distance from the centre of the Earth, not from the surface of the Earth. So you have to subtract the radius of the Earth. So our final answer for the height above the Earth is 21,000 kilometres. I want you to pause the video now and do these 5 questions and then come back for the answers. If you're unable to read that clearly, there is a version of it uploaded to Teams that you can use. So pause the video now. Are you ready for the answers? Mark your work, and if you get any wrong, make sure you work backwards to find out what it is you did. Ready to move on? Pause the video and do these 3 questions. Ready to move on? Pause the video again and do these 3 questions. Are you ready to move on? Pause the video one more time. This time, when you come back, you'll be able to mark them. Are you ready for the answers? If you can't see that because it's too small, there is a version of it uploaded that you can use. So pause, mark your work. Are you ready to move on? Now we're going to look at motion in a vertical circle. There are 2 examples that you're likely to see. In one of them, you've got an object going around the inside of a circular track. For example, the motorcyclist in the first diagram going round a loop-the-loop track. And the second one is an object being whirled around on a string. Now, in both cases, there's a constant centripetal force. So that's a constant force towards the centre of the circle, and that's what's causing the circular motion. There's also a constant weight acting downwards. So there will be a component of the weight contributing towards that centripetal force in some way. The other force, well, for the motorcyclist, it's the normal reaction force from the track surface on the motorcycle. And for the mass on the string, the other force will be the tension in the string. And you can try that out. You know, if you get an object, tie a string on it, whirl it around, you can feel that the tension isn't constant. The tension changes. And that's because the component of the weight that's acting along the radius, so a component of the weight that's acting towards the centre of the circle isn't constant. So let's look at the motorcyclist in a little bit more detail. So again, we have to remember, it's really important that we understand that the centripetal force is constant and that the weight itself is constant. What is changing is the size of the normal reaction force. So look at the second diagram. You can see the relative forces drawn there. So at position 1, the weight mg is acting directly downwards and the normal reaction force is acting upwards towards the centre of the circle. Positions 2 and 4, the normal reaction force and the weight are perpendicular to each other. And at position 3, the weight and the normal reaction force are both acting towards the centre of the circle. Now the centripetal force is the sum of these two forces. And the vectors, so the direction really matters. We're going to consider what happens at the lowest point and what happens at the highest point, because those are the areas that come up in exam questions over and over again. All right, for both cases, the centripetal force is the sum of the normal reaction force and the weight, taking account of their directions because they're vectors. So at the lowest point, that's position 1, the centripetal force will be the normal reaction force, that's Fn1, minus the weight, because they're in opposite directions. But at the highest point, the centripetal force is the normal reaction force Fn3 plus the weight, because they are in the same direction. I'm going to remind you again, because it's really important, the centripetal force is constant, but the normal reaction force is not. It changes depending on position around that circle. Now, if we rearrange these for the normal reaction force, that's the force you actually feel. So if you were sitting on that motorcycle going around that loop, the force that you would feel is the normal reaction force. So at the lowest point, the normal reaction force will be the centripetal force plus the weight. But at the highest point, the force that you would feel, the normal reaction force, will be the centripetal force minus the weight. So you would feel heavy at the lowest point. Let's move on and look at the same situation, but with the mass on a string. The physics is really similar, it's only the context that's different. So we still got the constant centripetal force towards the centre of the circle. The weight of the object on the string is not changing, that is constant. And the other force this time is the tension in the string. The centripetal force, again, is the sum of these two forces, and they're vectors, so we must consider their direction. So we're going to look at the same two situations, what happens at the lowest point and what happens at the highest point. At the lowest point, the centripetal force is the tension minus the weight because they're in opposite directions. At the highest point, the centripetal force is the tension plus the weight because they're in the same direction. And the tension is not constant. The tension changes depending on where that mass is around the circle. We're going to rearrange those for tension because the tension is the force that you feel when you're pulling that object around on a circle. So at position 1 down at the bottom, the tension is the centripetal force plus the weight. At the highest point, the tension is the centripetal force minus the weight. So you feel more of a pull at the lowest point. So the tension will be greatest at the bottom. So what about positions 2 and 4? They don't come up very often in exam papers. The tension and the weight are perpendicular. So what do you think happens there? Well, if the tension and the weight are perpendicular, the tension is entirely directed towards the centre of the circle, but the weight is perpendicular, so there is no component of weight in the direction of a radius, so the weight has no effect. In that case, the centripetal force would be equal to the tension. So in that diagram there, T2 would be the centripetal force. We're going to move on and do some exam questions. Now for these questions, feel free to pause the video, have a go at them yourself, and then come back and check your answers. Or if you just want me to talk through them, just keep playing. So the first one, we've got a ball of mass 250 grams swung in a vertical circle on a string of length 1.3 metres. The linear speed of the ball at the bottom of the swing is 4.2 metres per second. All right, let's pull out the data. So we've got M, we've got R, and we've got V. And I'm already saying to myself, if I know M, R, and V, I can do F equals mv squared over R. So that's going to be important. Right, the tension at the lowest point. So the tension is greatest at the lowest point. So it is the centripetal force plus the weight. So the centripetal force is mv squared over R. To substitute the numbers in, remembering the mass must be kilograms, I get 3.39 newtons. And the weight, mg, 2.45 newtons. So I have to add those together, and the tension at the lowest point is 5.8 newtons. Part B, to find the minimum speed of the ball where the string only just goes slack at the highest point. Well, the tension at the highest point is the centripetal force minus the weight, and the tension will be lowest at the highest point. So we have to say, well, at the highest point, if the string just goes slack, the tension will just instantaneously be zero. So just for that instant that the ball goes through the highest point, the centripetal force must be equal to the weight. So mv squared over R must equal mg. I can rearrange that. I can cancel off the m's from both sides. Rearrange to get v is the square root of R times g, which comes out to be 3.6 metres per second. Next one. Stone of mass 0.45 kilograms is swinging in a vertical circle of radius 75.0 centimetres. The linear speed of the stone is 6.21 metres per second. Have a think for a moment. How many significant figures should be given in the answers? I hope you all just said 3. All right, let's take the data out. Again, we've got M, R, and V, so I'm immediately thinking we're going to have to do F equals mv squared over R. Calculate the tension of the string at the lowest point and at the highest point. Well, at the lowest point, the tension is greatest, so I want to do centripetal force plus the weight. And at the highest point, the tension is the least, so I want to do centripetal force minus the weight. So work out the centripetal force, mv squared over R. Then the weight comes out to be 4.41 newtons. So for part A, add those together. For part B, subtract them. And then the last stage, round to the correct number of significant figures. Next one. A pilot of mass 58.0 kilograms comes out of a dive in a circular arc at a speed of 350 kilometers per hour. The pilot experiences acceleration of 9g. Let's take the data out of that one. We've got the mass, we've got the speed in kilometers per hour, but we need it in meters per second. So 350 kilometres, so I have to times by 1,000 to get that into metres. And that's per hour, so I have to divide by the number of seconds in an hour to get it into metres per second. Acceleration of 9g, well, g is 9.81, so I can convert my acceleration into metres per second squared like that. Okay, the upwards force applied by the pilot's seat. Well, that's going to be the value at the lowest point. So I have to add the centripetal force to the weight to get the maximum value. Now, I could stick in the numbers I've got. I could do F equals ma and then mg and add them together. But there's a bit of a shortcut here. Because m is in both of those, I can take m out and put the a plus g in brackets. And then it tells us the acceleration was 9g. So I can put 9g in instead of a. So that gives us that the force will be 10 mg, which comes out to be 5,690 newtons. You'd get the same answer doing it the long way round. So at the moment it looks like I didn't have to convert my acceleration. But let's wait and see what happens for part B. Right, for part B, to get the radius, I need to use a equals v squared over r. So I rearrange that for r, and I get v squared over a. This time I do need the metres per second squared value of a, because v squared, well, v is in metres per second. Substitute in, work it out, and I get 107 metres. Last one. The theme park Physics Fantasyland has a ride with a circular arc of radius 35.0 metres. You are sitting in a car that is just cresting the top of a ride. Okay, so we're going to take the data out of it and do a little diagram. So it looks like all they've told us is the radius. But for part A, the car is just cresting the top of the ride. So there's my little diagram. The car is going over the top of that bump. The radius of the bump is 35 metres. And part A, how fast must you be moving in order that you momentarily lift off your seat and feel weightless? So there's some hidden information there. They've told us the normal reaction force is 0. Therefore, the centripetal force equals the weight. mv squared over r equals mg. They've not told us the mass, but hopefully you can see why that doesn't matter. It cancels. So we get v squared over r equals g. If we rearrange that and substitute, we get 18.5 metres per second. Part B. Why do you think most fairground rides are designed so that there's always an acceleration towards the floor of the carriage? Obviously there are some exceptions. If you've ever been on air at Alton Towers and looked down, you might have a laugh at the number of shoes that are lying on the ground. However, all the area underneath it is fenced off and you can't go there. But that's not true for all fairground rides. If you drop something, you want it to stay on the carriage. Okay, well done. Now download and do the exam questions and self-assess your work using the model answers.